Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is about centre of mass. You'll be familiar with from the physics classroom of the experiment with a lamina, that's what that black outline represents, hung from one corner smoothly so that it assumes an equilibrium position hanging, and then be marked with a plumb line. And then you repeat the experiment, keeping the plumb line mark, and hang it somewhere else and get a second plumb line. And as a result you end up with a common point. If you repeat the experiment with other points, it's interesting to note that the plumb line always goes through that same point. So that point has a name, it's called the centre of mass. And intuitively it's the point where all the mass seems to be concentrated in terms of its contribution to weight, because that point always lies below, vertically below, the point which you use to pivot the lamina. Now that gives rise to our definition of centre of mass. We want to try and calculate where it should be. So we start off with the mass of a body distributed throughout the body. It's not a particle anymore, and for modelling purposes we define the centre of mass as the single point through which the weight force can be considered to act, and it doesn't matter what the orientation. We can treat the entire mass of the body as concentrated at that point. Now if it's a uniform rod, it's obvious where it's going to be. It will be at the geometric centre. If it's non-uniform, we have a calculation to do or an experiment. In centres of mass calculation we use, by convention, the x with a bar on the top for the x coordinate of the centre of mass. That can be generalised to y coordinate and so on, as we shall see. Now there's a basic setup with just two particles. The significance of this line is only that the particles lie on that line and they give us coordinates from the supposed pivot at the point at which we're taking moments at the end. Now if we take moments for those two weights, or two masses with weights m1g and m2g, the moment we'll get is m1g plus m2g each times the corresponding x1 and x2. That, if we're going to find the centre of mass, is good to give the same moment when we put the combined mass at the point where the centre of mass is supposed to be. So that will be times x bar. So we're looking for where is this point. Now first observation, if you can cancel the g's there, that means to say the value of g, essential to the idea of weight, doesn't actually contribute to the calculation. It's entirely to do with the geometric distribution of the masses, and that's important because it means we get the same answer on the moon. So we'll end up then with m1x1 plus m2x2 is equal to m1 plus m2x bar, and so we could divide by m1 plus m2 to get x bar is m1 x1 plus m2 x2 over m1 plus m2. Now what we're going to do is generalize that to any number of masses. You're going to have a string of products on the top and a string of masses on the bottom. So there's our general definition, and it's compactly summarized at the bottom. So we're going to say from that x bar is equal to sigma mi xi, sum of all the mass coordinate products over the sum of all the masses. Well, let's apply that to a particular case. Here we've got three uniform rods. Now for a uniform rod we can consider the centre of mass where all the mass is concentrated as at the centre, so let's just mark that with dots to start with, and similarly for the second one and the third one. So that distance will be 0.1 and this distance will be 0.3, and similarly there'll be a 0.5 for the third one. Now if we use a table, which is the easiest way of doing this, you're going to have three masses and three products. So those will be i's. So for our three masses we're going to have 0.04, 0.03, that's a 3, 0.02, and we're going to have coordinates 0.1, 0.3 and 0.5. So if we work those products out, we get 0.004, 0.0039 and 0.010. So the idea is that we add up the MX products, so we'll get 0.023, and we add up the masses, so we get 0.09. And so our X bar will be 0.023 divided by 0.09. So there we are, written out. Notice the first thing, that this slavishly applies the definition. We've got M1x1, M2x2, M3x3, and on the other side X bar times the sum of the M's. It's much easier to follow in the table, so that's a very important lesson to follow through. Anyway, the answer is there, worked out finally, at 0.256 to 3 significant figures, and we interpret that as saying that the centre of mass is 25.6 centimetres from A. So that's somewhere around about here. 25.6 centimetres means it's somewhere around about here, yes. 0.2 up to there, and 0.25 to 0.26 is a bit further along. So that's where we're saying the centre of mass is. Now let's take the more systematic approach to the table. We've got here a first example of how we can have a light rod which doesn't therefore contribute any mass, that's what we're assuming, with 3 particles stuck to it. And the particles are given masses 2, 3 and 5 kilograms, and the coordinate system x to the right, y upwards, so x this way and y that way are given in those terms. So what we do to do the calculations is simply transcribe the information given into the table, 1, 3 and 8, and so 2 1s are 2, 3 3s are 9, 5 8s are 40. So we end up with 51 divided by 10. So our answer for the centre of mass, X bar, will be 5.1, which is going to be somewhere around about here, isn't it? Well, that seems reasonable for that distribution of masses. It's somewhere notionally in the centre. So there's a slightly neater display of the calculations. It's dubious whether you need to write this out fully each time, because it's a common calculation that, and it's obvious enough what you're doing to say that X bar is simply 51 over 10 next to the table. So the coordinates of the centre of mass, finally our answer in context is 5.10. Now moving to 2 dimensions, we're going to change from having what we've already seen to the additional one for y bar, and you can imagine a third one for z bar if we went into 3 dimensions. So those are now going to be taken out as our definitions of the coordinates of the centre of mass for a system. So let's look at such a system. Well, our first step is to take in what we've got. You've got 4 points P, Q, R, S, each with its own mass, and you've got the axes as shown. You've got the coordinates also logged there on the left. So this one is 4, 2. This one is 1, 4. This one is 7, 3. And S is 10, 1. Why have I put those figures there? Well, because I want to refer to them compactly on the next slide. So there's the information. Now we transcribe what we've got. We've got P is 6 for the mass. We've got Q is 3. We've got R is 8. And we've got S is 5. And then for the coordinates, P 4, 2, Q 1, 4, R 7, 3, and S is 10, 1. So it's going to be 6 times 4 is 24, 6 times 2 is 12, 3 times 1 is 3, 3 times 4 is 12, 8 7s are 56, 8 3s are 24, 5 10s are 50, and 5 1s are 5. So then we want the sum of 22, 133, 53. So we can now write down that x bar, for example, is 133 over 22, and similarly for y bar. So there are our calculations more neatly presented. 133 over 22 and the 53 over 22, giving us the numbers from the calculator, and finally the answer stated in context to an appropriate degree of accuracy. So that's the essential lesson of that setup, that you use a table. It makes it much easier to avoid mistakes, to see what you're doing, and it's much easier for the reader, be that an examiner or somebody else, to follow what you're doing. So to sum up, if we've got one dimension, we simply use x bar is the sum of the mx products over the sum of the m's. If it's a light laminar, we can ignore the mass, and it's used to hold the particles in position, that's all. In the next video we'll be looking at laminas which do have a significant mass. If it's two dimensions, we have two definitions for x bar and y bar, and we could extend that to 3, or even in generalized terms to more. It's useful to arrange it's more than useful, I would say it's obligatory to arrange the calculations in a table to facilitate the working. Well, that brings us to the end of that video as a first introduction to centre of mass, and the next one looks at more complex situations, in particular where a lamina has a mass distribution of its own.